Our next speaker is Anuj Sarma, and he's going to be telling us about Zeeman effect observations in 36 gigahertz and 44 gigahertz methanol masers.
Okay, good afternoon. I don't think anyone will have a problem hearing me, but do you hear me through the microphone? Yeah. Okay, fantastic. All right, it's late in the day. It's late at the conference. And I know many of you are already starting to see those beers. That wonderful golden, amber, or dark, sitting in the glass. Maybe some of you are seeing the open arms extending and calling you there. In which case you have a drinking problem, but that is your issue, not mine.
Your time.
My issue is just to listen to Tim's words, where he said, you will finish this talk on time or else. Now you might say, well, Tim looks really friendly down there. He's not going to do anything. Yeah, but look at his hands. He's standing on a raised platform, and his hands indicate, you know, the fingers over there. He's going to throw people off the platform. So Laura, careful there. Next speaker, who is the last speaker of the session. Now it's a pleasure to be here, and I thank the organizers for giving me a chance to speak. I've just had some great news from the previous speaker, so this is good, because my news was going to be very dire, but will now be replaced by some of this good news. In any case, I don't need to say very much about the Zeeman effect, obviously, because Tom started the discussion yesterday. He certainly talked a lot about it already, so very informative. I should emphasize that the Zeeman effect is the most direct method for measuring field strengths, so it is certainly important for us. And again, I don't need to really emphasize this plot. Everyone's seen this plot quite a bit now, and you know what's all in there. The only thing I should emphasize is that this only involves the thermal lines, where you see the thermal effect. So there's a whole regime that goes off, oops, sorry, wrong thing. There's a whole regime that goes off this side at higher densities. That's not shown in this plot because this plot doesn't deal with that regime. And so the question then is, can we go to higher densities? And the answer is yes, we can with masers, because masers are very intense and almost point-like sources to our telescopes. They have very nice, strong profiles in many cases. And so the Zeeman effect in maser lines offers us the opportunity to measure magnetic fields at extremely high angular resolutions. Now, they say we should give examples from everywhere, but this time I'll just give an example from myself. This is work done in 2008. I realize I'm getting on in years. This is quite some time ago now. But as you can see, this is with H2O masers, which is not what I'm talking about here. But if you have the opportunity, so everything that's shown here within parentheses is a detected magnetic field in milligauss. I didn't put the, except for these two, which are upper limits, but all of these are detected fields in milligauss values. And so the idea is, if you have the opportunity to track fields across like this, it would be really great, because then you could kind of track the fields across all these regions at high density. Of course, in the Zeeman business, there's always good news and bad news. And the semi-bad news is, of course, the question that still remains unresolved is, do these high-density regions have these magnetic fields because of the very nature in which they are formed, or are these magnetic fields connected to the larger scales? That's a very, very ongoing point of discussion that has not been resolved. And so the question then is, what would bring me to a state of happiness in this field? And the idea is that what would bring me to a state of happiness is if we could find enough Maser sources, enough lines, where we could track this field and have examples of it for many, many different star-forming regions, so that we could say, we know, and there are already there are examples which I haven't put here, but there are some suggestions that indeed we know that there's some connection that these fields on these very small scales might have to the larger scale magnetic field, therefore that these are contributing. Now, how happy would that make me? Very happy. And as promised to certain members of the audience, as happy as Donald Trump if a wall spontaneously appeared on the southern border without having to pay for it. But moving on from this point, the specific thing I'm going to talk about is methanol masers, which of course the previous talk was also on methanol, so we have some background now to talk about this, but specifically I'm talking about, well, just of course to reiterate, methanol falls into two classes, class 1 and class 2. And class 2 is nearer to the protostar, whereas class 1 is farther away. So this is the way it was historically defined. Here is an example. Class 2 masers are nearer to the protostar, and then somewhere in the outflow. So we think that class 1 is a radiatively excited transition. Class 2 is a radiatively excited transition, and class 1 is caused by collisionally excited. Now, the next slide is not something I would show to this audience because it's too much of a detail, but it does, I do need to show it because I need to make a point. When we generate Stokes I and Stokes V, Tim, note, I have noted what they are. It's RCP plus or minus LCP. Yes, exactly. So I followed your advice there. When we generate that, in practice, the way we get the V profile or the magnetic field is by fitting the V profile to I itself and the derivative of I, and so it's this from this B we get this thing. So the line of sight field comes from that fitted value, but you need to know this, the so-called Z factor. Right? And that's been a source of frustration for many years now because we don't know this Z value. Right? A source of frustration not just for me, but this was revealed in a private email to me this morning, and it's been a source of much frustration. And I've tried to contact, I'm actually glad that you worked on, our previous speaker worked on this and actually promised us even both 36 and 44 because we have just not known this. In fact, I got so frustrated that I decided these days if you want to get work done on anything, you just call it dark. So I call this dark Z, and it looks like I succeeded because we now have a value for it. So this is good news, like I said. I should visit conferences more often, I guess. But anyway, so we did find this effect several years ago. I was working with Emmanuel Momjian. We found it in both the 36 and the 44 gigahertz. And then Wouter, of course, has been working on the class 2 sources, the 6.7 and 12.2. And that made me want to have a license plate with this thing on it. But then I realized the police might not be very happy if they saw this. So I decided to give up that idea. So then after that, so here's just, I'm sure I'm coming to the end of my thing. They say there was some blinking light that's going to come and shoot a laser at me and kill me or something. I don't see that yet, but I'm going to try and finish this up. Just 2 slides to show the results. Here's one example. This is an, oops, the wrong thing. This is, sorry. This is one example, and then we followed it up about a year later. You see how the maser intensity changes. It's the same maser, but the value of the detected Z below. Now, we haven't published this as a BLOS value because we don't know Z. So we have left it as Z times BLOS. So it gives us some idea of the magnetic field, and we can put in some test values for Z if we want to, but you can see where that would fall. For example, if you said Z was 1 hertz per milligauss, then B loss would be somewhere in the range of tens of milligauss or so, and then that would change depending on what your Z value was. So anyway, you see that these values remain the same. Here is a more updated example of this thing from the region DR. The previous one was from OMC2, which is kind of above the Orion Nebula, and then this is the other famous region, DR21OH. And again, you see that very nice profile there. Again, this value is a little higher. This is about 50. Again, this is ZB loss. So if you think of Z as being 1 Hertz per milligauss, that's going to be of the order of 50 milligauss or so. But like I said, of course, until we know the value of Z, that's not something we're going to be that we're going to put out there. So what are the final thoughts on this issue? Well, like I said, the first thing, Zeeman effect measurements in class 1, which we have done, class 2 maser lines. I've talked to Walter before, and in lots of places, so lots of good time. Zeeman effect measurements in lots of maser lines, and a vast repository of such Zeeman effect measurements, which then allows us to look at these fields all over. And then this line now, thankfully, someone finally figures out the value of Z, but as our previous speaker boy said, he has stuff for me, so I'm going to hunt him down after the talk and try and figure it out. And in the end, I'd like to, first of all, thank the Crutcher for giving me a postdoc and moving my career to its next level. And I'd like to thank Carl Heiles. I don't know what you're doing here, but I assume it's not illegal. But every time I have interacted with you, I've been a great beneficiary of the generosity of your time. So I thank you very much, and I thank the audience.
So, any questions for Anuj?
Yes, so, quick question: how stable were the masers over time?
Well, we haven't done time studies. The only one, I guess, you're asking about like over many decades or so. These masers are not, they're not highly variable. It's not like water masers. They're not very highly variable. We tracked this maser within about 2 years or so. They're reasonably stable, but we haven't followed. That's kind of the beta version of things where you then try to see if the field, how it changes, etc. But that's a much later study. I think we're still in discovery mode, I think.
Because we tried that with Alma on commissioning on the 95 gigahertz maser, and we saw high variability on time scales of weeks.
Or 95 gigahertz.
Yes.
Yeah. I know nothing about 95 gigahertz. These are 36 and 44.
Okay, more questions for Anuj? How about our previous speaker, Boy? Did he calculate these?
He said he has a calculation for 36 and 44.
Fantastic.
So after thing like exchanging notes, I'm going to change some notes.
Let's corner him afterwards.
Yes, let's corner him. Let's get him.
Good.
He can't escape.
All right, let's thank Anuj again.
Thank you. Oh, here's this part.